So this is part 2 of a series of videos to help you with the number patterns question in the exam. This time we've got a pattern that goes 5, 10, 20, 40. So it's clearly not going up by the same amount every time. So it's not an arithmetic sequence. So what's happening, you might notice that you're multiplying each term by 2 to get the next one. So it's times 2, times 2, times 2, and so on every time. So that's an example of a, that's an example of a geometric sequence. So write down in words any patterns that you observe. So whether it's an arithmetic sequence or a geometric sequence or any of the kinds of sequence that we're going to see in subsequent videos in this series, the structure of the question tends to be pretty much the same. So you might get, write down in words any patterns that you observe. So you might write each term multiplied by 2 gives the next term. So just putting that times 2 times 2 times 2 business into words. What else can we observe here? Each term is a multiple of 5, for example. I mean, they've got to be. If the first one's 5 and then we're getting all the other ones by multiplying the original 5 by something, then they're all going to be multiples of 5. But the key thing for that bit is to understand the command term right down in words. So they're looking for something in words, in plain English, and not some kind of an algebraic expression or argument. Okay, predict the next 4 terms in the sequence. So, well, we'll just fill that in on the table. So I'll write C table. So we're just going times 2 times 2 every time. So 40 times 2 is 80. Multiply that by 2, 160, then 320, then 640. So we're able to do that without having established a rule for the general term of the sequence. And that's the next bit. Find a general term connecting P and N. So that's really the bit that's hardest, and it shouldn't be too hard if you've got a good strategy for it. So let's think about this. So the first term is 5. The second term is 5 that's been multiplied by 2, 5 times 2. The third term has been multiplied by another 2 after that. So it's 5 times 2 squared, 5 times 4. The fourth term is 5 times 2 cubed, because you're multiplying by another 2 to get to that. And you start to see a link that they're all 5 times 2 to the power of something, and these numbers are going up by 1, but they're less than they're 1 less than the n number. So you would expect the 8th one to be 5 times 2 to the power of 7. And if you had to predict the 100th one, it would be 5 times 2 to the power of 99. So generally, it's always 5 times 2 to the power of something, and that something is always, wherever you are in the sequence, n minus 1, always 1 less than the position in the sequence. So got to write that down as a rule. So P equals 5, what did I say, times 2 to the power of n minus 1. So in fact, generally speaking, the nth term of a geometric sequence is always the first term multiplied by the common ratio to the power of n minus 1. So that is a general rule that you see in textbooks. Nth term of a GP, geometric progression, equals AR to the n minus 1. But of course, if you're just learning a formula like that, it's not as good really as understanding where that formula came from. And hopefully you can see by the reasoning I just went through over here why exactly it's 5 times 2 to the power of n minus 1. Okay, so we've got the good old test and verify bits. So these always have the same structure to them. So I'm going to say when n equals, well, testing it is making sure it works for the ones they gave you at the low end of the table, and then verifying it is checking that it still works for the higher ones where you predicted the values. So I'm going to test it for 3 and 4. So when n equals 3, for example, I'll just underline that. My rule says p equals 5 times 2 to the power of n minus 1, which would be 5 times 2 to the power of 3 minus 1, which would be 5 times 2 squared, which would be 5 times 4, which would be 20. And looking at the table, it is 20. So this matches the value in the table. I'll now do another one for n equals 4. So I'm just going to, whoops, press the wrong thing there. Change the 3's for 4's and everything that follows on from them. There we go. So if n was 4, my rule says p equals 5 times 2 to the power of n minus 1, which would be 5 times 2 to the power of 4 minus 1, which would be 5 times 2 to the power of 3, which would be 5 times 8, which would be 40. This matches my value in the table. So that's testing them, where you do it for the low values, where they've already given you both values. And the only difference with verifying is that you do it for a couple of higher values. So let's say you do it for 6 and 7. So when n equals 6, let me just delete all the 4's. When n equals 6, my rule says p equals 5 times 2 to the power of n minus 1, which would be 5 times 2 to the power of 6 minus 1, which would be 5 times 2 to the power of 5. 2 to the power of 5 is 2, 4, 8, 16, 32. So it would be 5 times 32, which would be 160. Table does say 160, so this matches the value in the table. Do one more for 7. Delete that and that and that and that and that. When n equals 7, my rule says p equals 5 times 2 to the power of n minus 1, which is 5 times 2 to the power of 7 minus 1, which is 5 times 2 to the power of 6, which is 5 times 2, 4, 8, 16, 32, 64. 5 times 64, which is 320. Table does say 320. This matches my value in the table. Okay, so same kind of structure to the question as when it was an arithmetic sequence in the previous video, with figuring out the rule, patterns in words, predictions in the table, finding, testing and verifying the general rule. So I'm going to go on to another example of that. So example 4, now the numbers are going down, but they're going down by a same certain ratio every time. So you might look at that and think you're getting from one term to the next by dividing by 2. But another way of looking at that is to say, instead of dividing by 2, you're multiplying by a half, or multiplying by 0.5. So you can still think of it as being in terms of multiplying by a common ratio to get from one term to the next. So write down in words any patterns that you observe. Each term is half the previous one, for example. Another pattern might be that the numbers are all even so far, but of course this will get down to a point where they're not even if you keep halving them. Oh, well, predict the next 4 terms in the sequence. I've just done that, haven't I? I've just filled that in. So see table. Find a general rule connecting P and N. Okay, so let's try and apply the same logic and reasoning as before. So the first term is 64. The next term is 64 times 0.5. The next term after that, you're multiplying by 0.5 again, or multiplying by half again. So you're multiplying 64 by 0.5 squared. And then the next one is just the previous one multiplied by another half. So it's 64 times 0.5 to the power of 3. And you can see they're all 64 times 0.5 to the power of something. So when you've got n equals 3, it's a 2 there. When you've got n equals 4, it's a 3 there. So if you had n equals 100, if you wanted to know the 100th one, then the number that would go there would be 64 times 0.5 to the power of 99, one less. So generally speaking, they're all 64 times 0.5, common ratio, to the power of n minus 1. So we should write that as a rule that says p equals something to do with n. So something equals something else. P equals 64 to the power of n minus 1. Okay, so good old test and verify again. So test, remember, is checking it works for the low values that are already given to you, and verify is checking that it still works for some of the higher values where you completed the table. So test your rule. Well, let's say when n equals 3, my rule says p equals 64 times 0.5 to the power of n minus 1 equals 64 times 0.5 to the power of 3 minus 1, which is 64 times 0.5 squared, which is 16. And at that point you could get your Desmos calculator to do that for you, and then just paste in the result from Desmos calculator in the exam situation. So when n equals 3, I get 16. That matches the value in the table. We need to make that observation. There could be a mark for that. This matches the value in the table. Okay, so that's testing, and then verifying is just doing it for one of the higher values at the top end. Let's do it for 6, where you filled in part of the table. So when n equals, I'm just going to delete some stuff here. When n equals 6, delete that, delete that, delete that. Okay, when n equals 6, my rule says p equals 64 times 0.5 to the power of 6 minus 1, which is 64 to the power, 64 times 0.5 to the power of 5, which is 32, 16, 8, 4, 2. And this matches the value in the table. So once again, you could stick this into Desmos calculator, paste it in the exam box, response box on the exam, and get the answer too, rather than having to spend too much time worrying about that calculation and trying to do it mentally. Okay, so that was geometric patterns. So that was part 2 of the series. Part 3 will involve quadratic patterns.